Hey, let's have a look at the properties of ionic bonds, sometimes simply known as salts. These are those substances that involve a metal bonded to a nonmetal. The metal loses electrons, the nonmetal gains electrons, rendering this positive, this negative, and then there's an electrostatic attraction between the two, forming a continuous lattice. One thing about salts is that they oftentimes dissolve in water. That means they break in half. It's interesting that they do that, and yet that's still considered only a physical property. I think if I broke in half, that would be more than just a physical change. Okay, what happens is water gets attracted to the positive parts. That would be the oxygen in water getting attracted to the positive parts. The hydrogen in water gets attracted to the negative parts, and that can form a intermolecular force that can overcome this electrostatic attraction, breaking it up, and then the water molecules will surround each ion. And be careful how you draw them. That's a typical question on a test. Always draw the negative part of the ion towards the hydrogen atoms and the positive part toward the oxygen atoms in water. We can write it like this. Sodium chloride in the solid form, in the presence of water, not as a reactant, so you write it underneath or above, can form the sodium cation and the chloride anion, which are now both aqueous. That's what the AQ stands for, meaning dissolved. And there you go. Another funky thing about ionic compounds is that they can form these huge straight fissures. When they're in this lattice, they have a perfect linear attraction of positive to negative. But if there is a frame shift, such as this, by an external form, every single attractive force becomes a repulsive force. Take a look at the fissure that's going to form right there, and that will form a crack in the form of a straight line. Another thing about ionic compounds worth knowing is how to name them. It's an unfortunate naming system if you ask me. It would be very simple if you always said how many of each there were so there's no ambiguity. However, they do not say how many of each there are. This is known as sodium chloride, which is fine, +1, -1. But perhaps you've learned by now that magnesium will ionically bond with fluorine, but it requires two of them. This will form a +2 ion. See where it is? It'll lose both electrons to attain that noble gas configuration. But each fluoride only needs to gain one, and therefore it's going to be MgF2. But we don't say magnesium difluoride. We say magnesium fluoride. And there it is. We can just write the charges as a personal note, drop them and switch them as a nice shortcut, and you get MgF2. The 2 goes over there. The 1 goes over there. We don't typically write the 1. And there you go. This drop and switch technique is a standard part of just about every introduction to ionic compounds. It's a quick way of drawing what they look like. You can also just explain it, right? You need 2 -1s to offset the +2. Let's try this. This person who's getting a really, really loose billet, which is typical of the French, is climbing on limestone. The chemical name is calcium carbonate. Let's try to draw it. Calcium is +2. The carbonate anion is -2. But it's not your garden variety anion, isn't it? Is it? It consists of 4 different atoms forming a -2 charge. There are lots of these. We call these the polyatomic ions. They typically show up in lists. I put them underneath my periodic table until students get used to them. And we got a good match here. One of each should be fine. CaCO3. The polyatomic ion is the carbonate dianion. Let's do some examples. Sodium cyanide has a polyatomic ion. Not sodium, but the cyanide is Cn with a -1 charge, +1, -1. That's good. Here we have calcium, whatever this thing is. Look it up if you need to. You'll find that that is a hydroxide. This is known as calcium hydroxide, not dihydroxide. We do not specify how many of each for the ionic compounds. These are some of the properties of salts, otherwise known as ionic compounds.